Hello, everyone. My name is John Holt, and I'm your host for today's episode of Eyes on Earth, a podcast of the U.S. Geological Survey's Earth Resources Observation and Science Center, or EROS, which is an acronym. Anyone who spends any amount of time here learns pretty quickly that we use a lot of acronyms. For example, we're the ground station and data archive for the Landsat series of satellites, and when we talk about them, we talk about their sensors. You know, the MSS, the TM, the TM+, the OLI, and the TIRS. Now, I'm not going to explain what all those are, but my point here is that we use these acronyms to simplify communication about the tools, concepts, and programs that we use every day. So one of our goals here at Eyes on Earth is to explain a few of those terms so that you too can partake in the alphabet soup that is Earth science. Today's flavor is NDVI, the Normalized Difference Vegetation Index. I know, but NDVI is super interesting. It's essentially a measure of plant health. How green are the crops, the forests, the grasslands? Satellites can track that every day, everywhere in the world. NDVI can help us answer all sorts of questions about how droughts, floods, wildfires, or seasonal weather patterns affect our food, our forests, and our lives. With us today to explain NDVI is Jesslyn Brown. Jess, welcome to Eyes on Earth.
Hi, John. Good to be here.
Yeah, so what is NDVI? What is this concept? Where did it get the name? Who came up with this idea?
All right, so NDVI, or Normalized Difference Vegetation Index, is one of a family of indicators, also known as vegetation indices. These are calculated from data collected from satellite sensors as a way to simplify looking at the Earth.
Okay.
So early in the days of working with satellite data, there was some realizations in looking at data that are collected in different parts of the electromagnetic spectrum. The red and the near-infrared part of the spectrum have specific and sort of predictable responses to vegetation.
Right, and when you talk about near-infrared, you're talking about part of the electromagnetic spectrum that we can't see.
Beyond what we can see.
Beyond what we can see.
That's correct.
Okay.
Right, so we see visible light is in the blue, green, and red. And just beyond red, a little bit longer wavelengths is the near-infrared.
These wavelengths are reflected, and we don't necessarily see them, but the near-infrared is reflected by vegetation, by plants.
The healthier and denser and greener, honestly, the vegetation is, the higher that reflectance becomes. So dead vegetation reflects at a lower amount of reflectance than green.
Right. So when we're looking at this, we're looking at the reflectance that we can't see, that's beyond the scope of our ability to see. And we are coming up with this index. It's essentially a math problem, right? That gives you this index.
Yeah. So this is the really geeky part, or one of the really geeky parts. The red part of the spectrum is highly absorptive. Green vegetation absorbs red light. That's why it doesn't look red. It looks green. When you get into the near infrared, you just see this high spike in reflectivity. The vegetation index was a way to simplify the information from two bands and utilize them together.
Two bands, the near-infrared and the red band. Okay.
That's right. So the first vegetation index was the simple ratio, which is just a difference of near IR and red reflectance.
One minus the other. Gotcha.
Right. But this needed to be normalized so that the measurements could be compared through time and across space. Normalization is accomplished through the sum of the red and the near IR. So really the math problem, as you call it, the algorithm, is the difference between the near IR and the red over the sum of the near IR and the red, NDVI. However, all of these are estimations of the surface, of the Earth's surface. And the vegetation indices in particular are not actually tied to any biophysical parameter per se.
Biophysical parameter, you mean?
I mean biomass, or something called LAI, which is leaf area index, vegetation cover density.
Right.
Those are all things that can be estimated with a VI, but they're not absolutely measured.
Right, so the VI itself doesn't tell you exactly how much biomass there is, how many leaves there are, but it's a way to...
It's a way to estimate it, and it's a way to look at it through time.
Each kind of plant, do they all have the same reading? I mean, it's a number, right? It's between -1 and 1. Do all plants have the same number if they're healthy?
Oh gosh, no. No.
Do only plants have an NDVI number? Does water have one, for example?
Yeah, so what NDVI over water tends to be very low, close to zero or negative.
Okay.
Snow also tends to be very low or negative. Bare soil, like a desert or rock, tends to be very low. We refer to this in our field as a qualitative indicator versus a quantitative indicator.
Okay.
So it has information. Low NDVI, we were talking about low NDVI. Low NDVI can be indicative of no vegetation or very little vegetation or senescent vegetation. And what I mean by that is, after the end of fall and all of the leaves have dropped from the trees and the grass, you will see a low NDVI. Compared to midsummer when the vegetation canopy is fully healthy, solid green, and that kind of thing. So that's that ability to track phenology. So what's kind of lovely and simple about the NDVI is that when it rises, vegetation's getting denser, and when it falls, this is looking at the same location, when it falls, vegetation's getting either dying off or getting less dense. That makes a lot of sense. So I think that early folks working in remote sensing were really attracted to this very logical pattern of NDVI across time.
Right.
It was easy to communicate. It was easy to understand.
We have talked in the past, Jess, about how NDVI is sort of like an ingredient, right? It's not, you don't just get an NDVI and this is the end point. What do you do with NDVI beyond just estimating how healthy the plants are?
All right, John, good question. So NDVI is ingested into a variety of operational applications. And what I mean by that is, providing information on a regular basis for a topical area that's important to people.
Okay.
One of those areas is famine early warning systems. The NDVI, it's calculated over the whole continent of Africa and actually a few different areas than that, and provided to the U.S. Agency for International Development to help them track and even possibly predict, but at least early detection of famine events, where in a continent like Africa and countries like Ethiopia or the Sudan, where people's lives are going to be in danger if they don't get access to food in a prompt way.
So this reading helps guide food aid and really save lives. This is part of what they're looking at.
Yeah, NDVI is just one ingredient of helping to figure out where to provide aid. But because we have satellite sensors, we can provide this information over broad areas and then combine it with, let's say, for example, a different indicator of rainfall or an indicator of evapotranspiration, how much moisture is being sucked out of the atmosphere, if you will, and put all those pieces of information together and say, yeah, this area is in trouble. And they also need to look at things like economic indicators as well. So NDVI feeds into something called FuseNet, the Famine Early Warning System Network. And when you're interested in figuring out if there's a famine or not, or a drought going on, you really want to know what happened in many years leading up to this year. How does this year compare to what you expect in a normal year, for example? NDVI gives you a building block for calculating a normal.
Right.
What is normal for this time of year? What is normal for July 1 or June 1? And what does it look like in comparison to normal? So again, where math is used to calculate a percentage or some sort of relationship to a normal NDVI signal, if you will, or a usual NDVI signal. Right.
And those anomalies are part of that, as you say, the mixture of information that goes into making a determination about what you're going to do.
That's right.
Okay.
That's right. Yeah, so some other uses for it. It's been used in health and epidemiology. As you said, drought detection, land degradation over time. All of these are kind of involve this time component in the study. Deforestation and just plain change detection and monitoring. So has the area really changed?
Right. And we're actually, we're recording in 2019. There are plenty of things going on in farm country in 2019. And we can actually see from NDVI, just comparing last year to this year, those signatures look vastly different because it's been a very wet year. There have been all kinds of problems. I mean, that's reflected, right? You can actually go and see what the difference is.
Well, that's one of the cases where you would want ancillary or extra information to help you with your determination, because extra saturated soils, for example, what we saw here in this region and just to the south of us this spring, where we had massive flooding and delay of the start of season due to some really late, very weird and broad snowstorm rain events, that's going to depress the NDVI, just like a drought is going to depress the NDVI. So you really need to bring in ancillary information to tell you what is the cause of the problem.
Right. So you can see that the readings are not as good, or not think that the plants are not as healthy as they were last year. But right. That alone doesn't tell you why.
That's right.
But it does give you an indication of maybe how broad the problem is.
That's right. You can see a spatial representation of where that is.
Now, how do I see that if I'm just a regular person, not a scientist? I mean, do they talk about this on the farm report? I mean, can I go and check this out somewhere? Is there a simple way to do this?
Well, we don't just send it out to the world.
Right.
NDVI goes out to the world. But there are some ways to get access to that information. You can download your components that you can make an NDVI from Eros, from our archive. That would take some work to do, and you'd have to have some specialized software to do that. There is a very nice online tool called Appears. And that tool will allow you to access NDVI from MODIS for this country, for the U.S., that we have also done some filtering and smoothing.
Sure.
We do that on a weekly basis, and there's a little bit of lag time, like a day or two, but then we put that onto Appears. So a person can log into Appears and bring up for their area of interest, an NDVI time series.
Essentially, anybody can go to Appears and there's a map and you can draw a square around what you want to look at. I mean, it's relatively simple.
That's right. You can draw a square, you can extract the data, which is actually data values that you can plot through time using something like Excel.
So there are ways to get at this information if you're
It's becoming
curious.
More broadly available, yeah.
We've been talking to Jesslyn Brown about NDVI. It's been a fascinating conversation. We hope you'll come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of Interior. Thank you for joining us.